Hello, in this video we will be looking at Taylor polynomials and Taylor series. Now this is just going to be a quick review of Taylor series, then we'll move on to Taylor polynomials and see some applications of Taylor polynomials. So recall that a Taylor series of a function f about a point x is equal to a is given in this form here. So we have two forms. First, we have the expanded form f of a plus f prime a over 1 factorial times x minus a, plus then we have the second derivative of f at the point a over 2 factorial times x minus a squared, etc. And this goes on to infinity. Notice that in each term in this sum, we have f prime, f double prime, etc. So the next term will be f triple prime at the point A. And also the denominator, so when we had a first derivative, we divide by 1 factorial. Second derivative, 2 factorial. Similarly, third derivative will be 3 factorial, etc. Also, when it was a first derivative, we multiplied by x minus a to the power 1. For second derivative, x minus a squared. Third derivative will be x minus a cubed, and so on. So this is a general term here. We take the kth derivative at the point A, divide by k factorial, and multiplied by x minus a to the power of k. So what we can do is combine this entire thing into summation notation, right? Represent the entire thing using summation notation. So k goes from 0 to infinity of f, well, the kth derivative of f at the point A over k factorial times x minus a to the power k. So basically we take the kth term and write it inside a summation. Now the reason why this works is because the first term here, notice I talked about the second term onwards, the first term does satisfy this because the zero derivative is just the original function, and also 0 factorial is 1 and x minus a to the power 0 is just 1. So we just end up with f of a when I take k as 0. When k is 1, we get this second term. When k is 2, we get the third term, and so on. Right, so both of these here are just representing Taylor, the general formula for the Taylor series of this function f. This point a is some specific point, some specific value of x in the domain of the function. And a is fixed. X here is a variable. It can vary, but a is some fixed value. Now, if we let a be 0, so the Taylor series is about the point x is 0 because a is equal to 0, we get what is called the Maclaurin series, which is a special Taylor series given here, where a is just 0. Right, both forms again written here. Alright, so consider some specific function. In this case, f of x is equal to e to the power of x, the exponential function. Note that this is a nice function because the general kth derivative is just the original function, e to the x. Right, so I could plug that into this general formula for the Taylor series, right, using the fact that any derivative is going to be e to the power x, right, or I can use the summation notation. Any derivative would be e to the power a because it's at the point a. Right, so we could factor out e to the power a if we wanted to and expand the summation like this. And this here is a general Taylor series expansion of f of x equal e to the power of x about a general point x is equal to a. If I chose a is a specific value, for example, a is equal to 1, then I would get this Taylor series. If I chose a is equal to 0, I would get the Maclaurin series, which is probably more noticeable or something that you might remember more. Right, general Taylor, well, the Maclaurin series for e to the power of x is just the summation of x to the power of k over k factorial. It's nice and simple, which most Maclaurin series tend to be. Alright, now there are many other Taylor series and Maclaurin series we could look at, but I will leave that up to you all to review those yourselves. Why are Taylor series important? Well, if we were to take the general Taylor series and take the first few terms of this Taylor series, we would get what is called a Taylor polynomial. So if I just leave out a bunch of terms and I just take, for example, the first 4 terms here, I would get a polynomial, which we would call the Taylor polynomial. And this allows us to approximate the function at a specific point x, whatever value of x we want. So the Taylor polynomial, the nth degree Taylor polynomial, is going to be the first n plus 1 terms. Right? Notice the first term is x to the power 0. So, for example, if I wanted 4 terms, I would have to stop at x to the power of 3. Right? So in this case, these 4 terms would represent the third degree polynomial because the highest power of x is a third power. So it's a third degree polynomial, but it has 3 plus 1, 4 terms. So just bear that in mind. So we normally denote this polynomial p subscript n. So p for Taylor polynomial and n is the degree of the polynomial. Now if we use this Taylor polynomial to approximate the function, then we would have some error because this is not going to be the exact value of whatever it is. So the error or remainder term is just going to be the original function, the entire function, minus the Taylor polynomial. So Rn, R subscript n, denotes the error term or the remainder term, and it's equal to the function itself minus the Taylor polynomial. Alright, so one other example here, going back to the Maclaurin series of e to the power of x given here. Suppose I wanted to look at 2 specific Taylor polynomials, the 2nd degree and the 5th degree, so P2 and P5. P2 means I have to stop at the second degree polynomial, so these 3 terms, and P5 I have to go up to the 5th degree, so that's these first 6 terms. So these are the 2 polynomials in question. Right? Suppose we wanted to use both of these polynomials to approximate e to the power of 0.1. Right? Meaning, if I were to take the exponential function and plug in x as 0.1, obviously I can use my calculator to work that out. But suppose I didn't have a calculator, then I can use these polynomials to approximate the value. So first of all, using P2, taking x as 0.1 in here, we get 1.105 as our approximation. Now note that the exact value of e to the power 0.1 is given here, right? This is not the full thing, it goes on beyond this, but 3, 6, 9, 10, 13, about 13 digits here, this is our value. Alright, so it's 1.105, 17, and it goes on. Alright, notice we have the same 1.105. Alright, the first 4 digits are correct. But it doesn't, our Taylor polynomial, the secondary one, doesn't actually give us the remaining numbers or the remaining digits. So it's not that accurate because it only gives us the correct answer to 3 decimal places. The first 3 digits are correct. Alright, it doesn't go beyond that. If we look instead at the 5th degree polynomial, P5, again, we take our P5 polynomial, substitute x as 0.1, and this is what we get. So we could compare this to the exact value. We have 1.105, 1709, 1, but then after that, this is different. So here we have a 6, 7, and here we have 8, and then some other digits. All right, so what this means is that only the first 1, 2, 3, 4, 5, 6, 7, 8 decimal places are correct. Right? Both of these, if I rounded them off, I would get 1.1051792. So both of these are basically correct to 8 decimal places. Right? The first 8 decimal places are good, but beyond that, they don't match up. Because, for example, if I went to 9 decimal places, this would end in a 7 if I round it off. Whereas this would end, this would end in an 8, which is different. Right? The exact value should be an 8, but this would give me a 6 or a 7 depending on whether you round off or not. So it's different there, so we say that it's it's different in the 9th decimal place, so we say it's accurate to 8 decimal places. All right, so note that, just a side note here, I could only estimate the, well, in this particular example, I estimated the degree of accuracy using the exact value. Now, what we are concerned with is actually estimating the degree of accuracy of approximations without knowing the exact value. So we'll see how we do that later on. All right, now this theorem is going to be very useful for that, and that is called Taylor's theorem. What Taylor's theorem is, it does, or what the theorem says is, if we have a function f where all its derivatives up to and including the n plus 1 derivative exist in some open interval around a point in question x is equal to a, then for each point x which is not a in this interval, open interval, there exists some value xc, right? This is pronounced different ways. I pronounce it xc, some people pronounce it xi. Alright, so xc lying between, strictly between a and x. There is some value here for xc lying between a and x such that the function f of x is equal to the Taylor polynomial of degree n plus this term here. Right, so we know what the Taylor polynomial Pn is. This term here, so we have the n plus 1 derivative of f at a point xc over n plus 1 factorial times x minus a to the power n plus 1. Alright, now what that means is, remember, if you remember, the error term is f of x minus Pn of x. So the error term is really just this term that we added on here. Alright, so the Rn of x is just this term. Now, I put the coloring in here to kind of help you remember this a little better. So remember, for the Taylor polynomial of degree n, we have the function and its derivatives at the point a. The denominator from the second term onwards is 1 factorial in the denominator. Whatever the derivative is, we divide by that number factorial. So second derivative, 2 factorial, nth derivative, n factorial. And then we multiply by x minus a to the same power. So x minus a to the power 1, x minus a to the power 2, and so on. Right, so that is how we got Pn. Now this error term here, what we do is, notice Pn stops at the nth derivative, and this is x minus a to the power n. We have n factorial down here. What we essentially going to do is imagine what the term after this in this polynomial would be. The term after this would be the n plus 1 derivative at the point a over n plus 1 factorial times x minus a to the power n plus 1. So what we're going to do is take that, and the a that we would have gotten inside here, we replace it with xc. And that is what the error term is. So essentially, it's the n plus 1 term in the Taylor polynomial, but the last term in the Taylor polynomial if we were to go one higher, but instead of taking this term at the point a, we take it at the point xc, which we don't know, but the theorem says that this xc exists such that this is true. Now you're not required to know the proof of this, right? I believe the proof is given in the reading material, but all you need to know is how to use the theorem. Alright, so like I said, xc is some number lying between a and x. Now, a and x, you could have the two possible cases, either a is less than x or x is less than a. In both cases, just remember that xc lies between the two numbers, whatever they are. Alright, also a note, this form of the remainder term is called a Lagrange form. There are other forms of the remainder term. This is the one that we are looking at. Alright, now this xc, Taylor's theorem tells us that it exists. Right, there exists a value xc. Taylor's theorem tells us that this exists. It does not tell us how to find it. And in fact, we will not be interested in how to find it. Alright, just a few things to note. The value of xc does change with all three of these, with x, with a, and n. Right, so if I were to vary the value of x, I would get a different xe. If I vary the point at which it's centered a, again, different xe. If I change the degree of the polynomial I'm looking at, obviously I'm going to have a different error term, so a different xe again. Alright, so let's go back to the example we looked at before. We have the function e to the power of x. Remember, we already saw that if I wanted to estimate the value of e to the power of 0.1 using p2, I get 1.105. Now, Taylor's theorem says that using a is 0, right, because this is a is 0, this is Maclaurin series, or for the Taylor polynomial from the Maclaurin series. So using a as 0, Taylor's theorem tells us this, right? The only difference here is that this would have been x minus a to the power n plus 1. Now a is 0, so it's just x to the power n plus 1. If we let n be 2, because we are looking at p2, so we let n be 2, this is what we get. Right, which simplifies to this, because I know that regardless of what xe is, the third derivative of the function with respect to x is going to be e to the power x, and I could plug in that value xe. Right, so we substitute n as 2, and we substitute what f of x is, and this is what we get for our error term. Right, now what we can do is in this entire equation, I could substitute x is 0.1. So on the left hand side, I get e to the power 0.1, which is what I want to find. P2 of 0.1, we know that value is 1.105. And simplifying this, we get 1 over 6,000 times e to the power of xe. Notice that there is only one variable in this equation, or one thing that we do not know, which is this xe. Everything else is known things, known values. Right, now suppose I were to use a calculator, I could solve this equation, right, because xe is the only unknown. I could solve this equation and get a value for xe. Right, don't worry about this value. We're not going to do this when we're actually working with problems. Just note here though that this value that we could get if we solve the equation does lie in the interval that Taylor's theorem says it should lie in. It should lie between a and x, and it does. Right, so like I said, we are not concerned with finding the value. This was just an example to show you that it could be found if you use a calculator. Right, what we are concerned with in this course is to use Taylor's theorem, right? Use Taylor's theorem and then be able to find bounds, or to find an interval containing xe. Right, and then use that interval to figure out, well, what is the maximum error I could have and what's the minimum error? And then that will tell me how accurate my approximation is. Right, because remember, what we're doing here is we're taking our polynomial, we will be able to find a value. This, once we substitute the value for x, this will give me a number. And we need to figure out some error term here. Now, whatever this error term is going to determine how accurate this number is. Right, so imagine if this error term were really big, right, then this number that I got, it means that is not very accurate, right? If this error term is very big, meaning that, for example, let's say this error term could have been as high as 0.1. It means that I don't really know what's going on here, because I'm not even sure what's happening even up to the first decimal place. Right, but if this is very small, let's say the error term, the largest possible value this error could be is like 0.00001. What that means is that this approximation is going to be very good, because the error term is very small compared to whatever my approximation would be. All right, well, when we do an example, you'll see that a little more clearly. All right, now I'm actually going to skip this example, go on ahead, we'll do the second example and then come back to this, because this one is a little trickier to explain. This one here is much more straightforward. So what we want to do is we want to prove this equation first of all. Right, we want to prove that this is true where xc is some value that lies between 0 and x. Now from the time you see this, you should kind of think, okay, this looks like it could be coming from Taylor's theorem, right? And in fact, that is how you would prove this. You would prove this equation using Taylor's theorem. All right, so if we go back to Taylor's theorem, that's this thing here. All right, Taylor's theorem says I can take my function f of x and write it like this. Notice there's the xc term here. So if I want to use Taylor's theorem, I need to know three things. Right? I need to know what is f of x, what is the value of a if there's a value, and lastly, what is n, because I'm going to need to know which polynomial I'm working with. Right? So the very first thing you should do is identify those. Notice that the question does not tell you anything about f of x. There's no f of x here. So that's the first thing we need to do. We need to identify what that is. And f of x will always be, well, usually be whatever's on the left-hand side of this equation. You can easily just let that be f of x and be able to prove this equation using Taylor's theorem. So we can let, notice I said let f of x be cos of x, because that was not given in the question. The second step, right, and I've laid it out in steps for you to hopefully help you easier understand what's involved so you can remember how to do this on your own. Second step, as I said, we need to know what a is and what n is. Now an easy way to determine what a is, well, two things. Notice there's between 0 and x. Remember, xc always lies between a and x. So if you see between something and x, this something is going to be a. The other way to determine what a is to look at the powers of x. If you see like x minus 1 squared and then x minus 1 to the power 4, it means a is 1. Whatever you're subtracting from x, that is a. If there's nothing being subtracted from x, then a must be 0. Right? So two different ways you could identify what a is. Right? So a is 0. You don't need to justify that, you just need to state what it is. The last thing we need to identify is what is n. Now the most accurate way, in my opinion, to identify what n is again to come and look at this last term and look and see what the power of x is. Whatever that power is, you're going to subtract 1 from it. Right? The reason why we are subtracting 1 from it is if you look at Taylor's theorem, the last term always has n plus 1 as a power. So if I know what the power of the last term is, the term with xc, I look for this power and I subtract 1 and that will give me n. Right, so in this case, n, because the power is 4, n will be 3. So we know what f of x is, we know what a is, we know what n is. Now we can go and use Taylor's theorem. So the third step would be to write what Taylor's theorem is for these particular things. Right, I would leave f of x in, but specifically for the values of a and n. So you state Taylor's theorem for those two values, so a is 0, n is 3. Now, using n as 3, it means you have to state the Taylor polynomial of degree 3, so you have to go up to x cubed, and then you have your error term. Remember, the error term has xc instead of a, right? A is 0, so that value is substituted here. Right, remember to write that xc lies between whatever a is and x. Alright, now what we're going to do is use this is given, right? This is Taylor's theorem. Taylor's theorem says this is accurate, this is true. So we're going to use what we know is true and try to prove this thing. How we're going to do that is we're going to take f of x now and substitute it into this equation. Now if I'm going to do that, I will need to know what the derivatives of f are. First I need to differentiate and then I need to substitute the values. So I'm going to need to know up to the 4th derivative. So I take f of x and I differentiate 4 times and I note those. And then I can substitute. So I need to know what f of 0 is, f prime 0, f double prime, triple prime. But be careful, the last one is the fourth derivative at xe, not 0. So for all of these, you'll have values, except the last one will be a function of xe. So we're going to take these and substitute them into this equation, right? Note that f of x is equal to cos of x, right? After we substituted, this is what we get, and then we can simplify. We end up with 1 minus a half x squared plus 1 over 24 cos of xe x to the power 4, which is exactly what we needed to prove. Right? Always double check, make sure that you have what you're supposed to prove. Make sure that everything matches. Also, like I said, remember to mention that xe lies between 0 and x. Right, now that completes the first part of the problem. Right, now when you're doing this, a question like this, I see it happen sometimes where students are tempted to use whatever is given later on up here. Do not do that. Right, this should flow in order. So the first part should be done first, and then you use the first part to do the second part, and so on. The second part now says using this, you can basically using this thing, this equation with this result, estimate cos of 0.1 and determine the degree of accuracy. So we'll see how to do that. Now, cos of 0.1, this 0.1 is in radians. Again, unless I specifically tell you that it's in degrees, the value is always going to be in radians. Alright, so we'll do the second part. So the first thing we need to do is take the equation that we had and substitute for x. Right? Sometimes you have to determine what x is. So compare this. I have cos of x, and I want to find cos of 0.1. Right? Cos of 0.1. If I want to do that, then I need to let x be 0.1. Be careful, x is not always going to be this value. In this question, it is, because it matches up nicely. If, for example, there was a 2x here, then I cannot take x as 0.1. I would need to take x as 0.05, because 2 times 0.05 will give me 0.1. Right, so we substitute the value for x. Right, now we already have a here, so we don't need to substitute that again. We plug in 0.1 and we simplify. Again, once you do that, you should have the first few terms, that's these two, reducing to a number, and then the last term here, the error term, will have cos of xc in it somewhere, right, times something. Right, remember xc lies between 0 and 0.1. So that's the first step of this part of the problem. This 0.995 is going to be my estimate. Alright, this is what I'm going to say my estimate is. Remember, it's this plus your error term. So this is my error term. What I need to determine is how big is this error term? What's the maximum value this could be? Right? Also, sometimes what's the minimum value? Now, I don't know what xc is, right? So I don't actually know what value this thing is. But remember, cosine is a bounded function. Cos of any value will always lie between -1 and 1. And in fact, if the value is in the first quadrant, right, if xc is, let's say, it's some value between 0 and 90 degrees, or between 0 and pi over 2, then cos of this is always going to be between 0 and 1. Not -1 and 1, but 0 and 1. I could make that restriction on it. Right? That's just stated here. Because this angle xc is between 0 and 0.1, obviously it means that it's between 0 and 90 degrees, or 0 and pi over 2. Which means that cos of that angle will be between 0 and 1. This we know for a fact. It does not matter what the value of xc is. This must be true. Now, because this is true, I can use that to estimate how big this error is, right? I need to multiply cos of xc by this value, so I can just multiply this entire inequality by that number. So 0 times this is just 0. This number times cos of xt gives me the error term. And then 1 times this number is this. Now what I have here, this inequality gives me bounds for my error. My error has to be greater than 0 and it has to be less than this number here. Right? The error is some value between these two. So what I'm going to do now is use that fact that I have bounds on both sides for the error to see how accurate this is going to be. Now the easiest way to do that is to take this number and add both of your bounds to that number. So you take this number and add the lower bound, so you'll get 0.995, and then you take the number and add the upper bound, which is this, and you get 0.99501 04167. Now what you're going to do is compare these two numbers to see what kind of variation or what kind of range of values you could get for the actual answer. Right? The actual answer meaning what are the possible values that this thing could be. Cos of 0.1. So cos of 0.1 is going to be some value between these two numbers. Notice that if I compare these, the first 4 digits, right, 0.9950, there's a 0 after this, I have a 0.9950 here as well. But the fifth digit is different. The fifth digit could be a 0, it could be a 1, it could be a 2, it could be a 3, up to a 4, right? It goes from 0 to 4. So the fifth digit could be any one of those, meaning I do not actually know what the fifth digit is. What that means is that my estimate is going to be 0.9950, right? You could leave out the 0 and just write it as 0.995. But when you're stating the degree of accuracy, because we know it's 0.9950, our answer is going to be accurate to 4 decimal places, right? Not 3 decimal places, right? It's not just 3 decimal places, it's accurate to 4 decimal places. Because regardless of what the actual value is, it's going to be something that starts with 0.9950, and then after that 0, we don't know what it is, but we know that it starts with 0.9950, so we know the accuracy to 4 decimal places. Right? And that is how you would, in my opinion, that's the simplest way to determine what your accuracy is and what your estimate is. Now the last part is to find the Maclaurin series for cos of x. So what that involves is taking the Taylor series that you would have gotten, well, the terms of the Taylor polynomial, and writing out basically the general term and then substituting a as 0. So if you come down here, we already found, this should be a comma here, f of x, f prime, f double prime, etc. We can substitute the value for a. Right? This time we substitute in a as 0 everywhere. We're not worrying about any xe. Right? This is the Maclaurin series, not a polynomial. So the series goes to infinity, so there's no error term involved there. Now whenever I ask you to find Maclaurin series, I'm expecting you to find to list out the terms, and if possible, write it in a nice concise form. With cosine of x, there is a nice concise form given here, so I'm expecting you to give that. Right? The sign alternates. It's, well, a plus, then minus, plus, minus, and you get that by using minus 1 to the power k. Notice there are only even powers of x to the power 0, 2, 4, etc. So x to the power 2k. And then also the denominator is whatever the power is, factorial. Right, so this is the Maclaurin series for cosine of x. Right, now coming back to this question, I'm going to go through this pretty quickly. I'm going to leave it up to you to do the first part of it and make sure it's done correctly. So this time we want to prove that sine of x is equal to this long thing. Now this time, notice there isn't a value for a. I just have an arbitrary number a. Right, so you don't have a specific value to substitute this time. Right, but off the rip, I know that f of x is going to be sine x, Right? I don't have a value of a, so I have to leave that arbitrary. And also n is going to be 2, right? Because I take this highest power, well, the power corresponding to this term, and subtract 1 from the power. So f of x is sine x. There isn't a specific value for a, but we know n is 2. So what we do is we state Taylor's theorem using an arbitrary value, an arbitrary constant a, and we use n is 2. This is Taylor's theorem here, right? Where x lies between a and x. We find the necessary derivatives. We substitute for a and xe, right? The last one you have to substitute xe, the previous one you substitute a. And then we take these and substitute them into Taylor's theorem. Right, that gives us this expression or this equation here. We can simplify it. Well, actually, this is after you've simplified it. So this is the equation we wanted to prove, and again, x lies between a and x. That's the first part of the question. The first part is always going to be pretty straightforward. You simply follow these steps to use Taylor's theorem to prove the equation given. Now the second part for this problem is a bit more complicated because I give you the value for x in degrees. Right? A, I give you it in radians, but x, I give you it in degrees. So what you're going to need to do is convert this angle from degrees to radians. Right? So we know A is pi over 4, but 51 degrees, when x is 51 degrees, we want that in radians, and you do that, you convert it to radians by multiplying by pi over 180. Right, multiply by pi over 180, simplify it. In this case, it simplifies to 17 pi over 60. Right, and then we take, so we would take this value for a, we take value for x, and substitute it into this equation. Now, if you're going to do that, notice there's a x minus a 3 places, so it'll help if I can work out x minus a and simplify it. In this case, pi over 30. Also, I'm going to end up with sine of a and cosine of a, sine of pi over 4 and cosine of pi over 4, so it'll help if I know what those are. Right, sine 45 degrees and cosine 45 degrees both work out to be root 2 over 2. So plugging all of those into the equation that we have, and again, this equation, remember, it's the equation that is given in the question. So this is something, even if you can't do the first part of the question, you can always do the second part by substituting the values and working through it. So we simplify the first few terms, we get this number here. Also, please always write your number here to at least, well, to as many decimal places as necessary. So how I usually do it is I would look at the error term, look at the simplified number in the error term, make sure that this number has at least 3 significant figures, right? So this actually wrote it to 5 significant figures. 1, 2, 3, 4, 5. And then you count the number of decimal places that you need there. So I actually have 8 decimal places here. If I have 8 decimal places here, I want to write this number to 8 decimal places as well. Because remember, we're going to be adding these things at the end. Right, so this is my estimate. This is my error term. Notice my error term has a negative sign here. Also, xe lies between a and x. A is pi over 4, which is 45 degrees. And, well, we know x was 51 degrees. So xe is some value in degrees between 45 and 51 degrees. The important thing about that is, again, it's going to be between 0 and 90 degrees, so it lies in the first quadrant. So once again, I can use this. Cos of xe lies between 0 and 1. And now I need to multiply by this number. Note that there's a negative sign here. Right? So after I multiply by this number, my error term actually lies between 0 and negative of this value because of the negative sign. Well, negative 0 is still 0, right? So these are the bounds for my error term. So what we're going to do is take our estimate and add these bounds to it. Right? Once we simplify, we get that our actual answer is going to be some value between these two numbers. So what we're doing again is we're comparing the digits to see which digits how accurate both numbers are. Well, or a better way of saying it is we compare to see, well, how many decimal places I can go to so that both numbers are the same when I round off to that number of decimal places. So I go as far as I could. Notice if I go to three decimal places, I get the same number. But the fourth decimal place could be different. It could be a 0, it could be a 1, or it could be a 2, or even a 3 when you round off. Right? So we don't know what the fourth decimal place is. We only know that the first three decimal places are sevens. So therefore, we would say that our answer is approximately 0.777, correct to 3 decimal places. Right, now again, the Maclaurin series, this time we want the Maclaurin series for sine of x, which works out to be this. I'm not going to go too much into this in this video. That's not the main purpose of this. Right, now there are a couple more questions here. Let's see, we have 1, 2, 3 more examples. These are a little trickier, but I don't want to make this video too long, so I'm going to stop this here. These examples we will go through in class, right? But make sure you at least take a look at them first so that when I explain it in class, it will be much clearer and hopefully clear up any issues or misunderstandings that you would have had. All right, so I'm going to stop this video here, and I will see you all in class.